Solutions of the critical p-Laplace equation. So thank you, Alberto, when you want.
Okay, thank you, Joaquin, for the introduction, and thank you, Miguel, for this opportunity. It's a real pleasure, and I'm very happy to give this seminar in my department, actually. And okay, as Joaquin said, the title is a classification of solutions to the critical p-Laplace equation. And as you can read, this is based on a joint work with Giulio Ciraulo from the University of Milano and with Alessio Figalli from the ETH in Zurich. So let's start. So we are interested in classifying positive solutions to the so-called critical p-Laplace equation. So this is a very important equation in the PDE world, but also in the geometric analysis world. And so for n bigger than 2, and for p between 1 and n, the equation is the following. So we have the p-Laplacian of u plus u to the power p star minus 1 equals 0. And we are interested in entire solution, so defined in all Rn. And as I said, positive solutions. Okay, so this is our problem, and of course this so where the p-Laplacian is the usual p-Laplace operator, so the delta p of u is nothing but the divergence of the norm of the gradient to the power p minus 2 times the gradient of u. And for p equal 2, of course, we have the usual Laplacian, and the exponent p star is the so-called critical exponent for the Sobolev embedding, so it's very important, and is given by n times p divided by n minus p. Okay, so these are the two characters of the story, and let me call this problem P, blue P. And so this problem is very important, and then has been really studied a lot, because it is known that P, so blue P, is related to two important problems, and one comes from the, let's say, PD side, which is the study of critical points of the Sobolev inequality. And the second one comes from the, let's say, the differential geometry world, which is the Yamare problem. Okay, so let me try to explain you these two problems. So, of course, so the first one, we start from the Sobolev inequality. Okay, it is well known that there exists a constant such that we can control the LP star norm of a function in Rn with a constant time the LP norm of the gradient in Rn. Okay, this is the LP star, of course. We can control the LP star norm with the LP norm of the gradient. So, of course, one is interested in the best Sobolev inequality, so the sharp Sobolev inequality, so the role of this constant is important. And if, let's say, the constant C is given by the infimum of a functional j of u, where this functional is nothing but the quotient of the two LP norm. So it's the gradient, the norm of the gradient in LP divided by the norm of u in LP star. Okay, so if the constant is given by this this infimum, then the Sobolev inequality is the optimal one, the sharp one. And of course, here you can see that we have we have to study the infima of this functional, but if we look for stationary point or critical points, so not only minima, let's say with u positive to simplify a little bit the notation, then we have to compute the first variation of the functional. So we compute the derivative with respect to epsilon, evaluated at epsilon equals 0, of the functional j of u plus epsilon phi. This is equal to 0 for all phi, let's say, test function, so C infinity with compact support in Rn. Okay, so this is the usual Euler-Lagrange equation, and this leads to, so this is equivalent to the following integral formula. So we have the integral over Rn of the gradient of u to the power p minus 2, gradient of u, scalar gradient of phi, minus, here we have a constant, but is not important actually, the gradient in Rn of u to the power p star minus 1, minus 1 times phi equals 0. So, and here there is this constant alpha, but up to consider, instead of u, lambda times u, we can assume that this alpha is 1. And so this is exactly, with alpha equal 1, the weak formulation. The weak formulation of our problem P. Okay, the p-Laplace equation, the weak formulation is exactly this one. So our problem P arises in this context, and arise also in the Yamabe problem. So of course it is well known, but let me recall very briefly this. So the Yamabe problem actually is no more a problem, but is a theorem. But so the theorem was let's say was proved by different people in different years. So it was stated by Yamabe in the 70s. Then there is a contribution by Trudinger in 68. Then by Aubin in the 76th, and finally by Schoen in 84. Okay, so this is a Yamabe theorem, and so given a Riemannian manifold and G0 with a Riemannian metric G0, so a compact Riemannian manifold of dimension bigger than 3, of dimension n bigger or equal than 3, then there exists a new Riemannian metric G conformal to G0, such that the scalar curvature of M with respect to this new metric G is constant. Okay, so this is the Yamabe theorem. And okay, where is the PD side of this theorem? Of course, there are many ways to write this this conformality. So if the new metric G is u to the power 4 divided by n minus 2, the old metric, then solving this problem. So finding this metric G is equivalent to solve this PD, then you solve this problem. So we have 4n minus 1 divided by n minus 2. The Laplace Beltrami with respect to G0 of U minus the scalar curvature times U plus, let's say, the constant times U to the power n plus 2 divided by n minus 2 equals 0. Okay. And okay, let me observe that this exponent here is nothing but 2 star minus 1. So this seems, here we have the Laplacian, the Laplace-Beltrami, and here we have the right exponent. So to simplify this, this equation, of course, one can consider the round sphere. So if mg0 is the round sphere, then by applying the stereographic projection, we can, let's say, project this equation in Rn. So then we have exactly this equation. The Laplace-Beltrami becomes the usual Laplacian plus Rgu to the n plus 2 over n minus 2 equals 0 in Rn. Okay, so this is up to constants, of course, our equation. So this is our problem P with P equal to, so for the Laplacian. Okay, so this introduction was to motivate why this problem is important. And so, as I said in the title, we are interested in a classification result for solutions to this problem. So we are interested in what is called the Liouville type theorem. So let me just, so the key observation is the following. So an explicit family of solutions to our problem, so it was the p-Laplacian of U plus U to the p star minus 1 equals 0 in Rn, positive solution, is given by the Aubain-Talenti bubbles. Okay, so these functions are a two-parameter family of functions. So U lambda x naught. So lambda is a number and x naught is a point in Rn. And let me put here a p to remember that in the problem there is the parameter p of x. So they are given by, here we have a constant which depends on lambda, on n and p, which is not important. And on the denominator we have lambda to the p over p minus 1 plus x minus x naught to the p over p minus 1, everything to the power n minus p over p. Okay, so one can check this, that this kind of functions satisfies our equations. Okay, are radial functions, let's say with center at this point x naught. So this x naught will be a point in Rn. So the natural question is true that if I consider a solution to this problem, then is given by an Aubain-Talenti bubble. Okay, so these are particular solutions. It's true that these are all the solutions. So the desired theorem, should be something like this. So every solution to our problem P is given by an Aubain-Talenti bubble. Okay, and So before showing you the literature related to this theorem, let me mention that these functions are called Ovent-Talenti bubbles because in two independent paper, Oben and Talenti, in the 76th, showed that this kind of functions, so these functions here, realizes the equality in the Sobolev inequality. So, in particular, they are the infimum of this of the functional that I brought before. So this theorem would have an important implication in this context because if this theorem is true, then this will give a complete classification of extremal points, and actually you would say that all the extremal points are minima. Okay, and on the other side, regarding the Yamabe problem, a theorem like this would give a complete classification of metrics in the Euclidean space, which are conformal to the standard one and with constant scalar curvature. Okay, so let me illustrate the state of the art related to this theorem. So the state of the art is the following. So of course the first case that has been studied is the case p equal to, so the semilinear equation for the Laplacian. And for p equal to, the result, the Liouville type result, was proved by Caffarelli, Guidas, and Sprack in '89. And actually, there is also a paper by Guidas and Nirenberg, which is very important, in '81, so it's before this paper, but they proved the theorem with this additional assumption, so that U of X is a big O of the fundamental solution for X large. Okay, so they assume this condition, but so this is an important paper in the PDE world. Okay, so then the case, the general case. So for P between 1 and 2, this was proved by Vetois, Jérôme Vetois, in 2016, and the case P between 2 and n, so the remaining case, was proved by Berardino Schunzi, always in 2016. But an important difference is that in these two results, so for, let's say, for the real p-Laplacian world, so they assume, so with the hypothesis, U in this space D1P of Rn, which is the space of U in LP star of Rn, such that the gradient of U is in LP. Okay, so this is in some sense a natural assumption, because in the Sobolev inequality we are saying that the two sides of the Sobolev inequality are finite. So it is natural in some sense to assume that U is in this space, but trying to prove the same theorem, so the same classification theorem without this assumption, so as in the case P equal 2, is a challenging problem, is an open problem, and it would be very interesting to prove it. Okay, so this is the big difference between the case P equal 2 and the, let's say, the quasi-linear case. And okay, a crucial tool to in the proof of the previous result is the method of moving planes. The method of moving planes, of course, it is well known and was introduced by Alexandrov in a different context to prove the soap bubble Alexandrov theorem in '56, and also in the PD context was introduced by Serrin in '71. Okay, And okay, a remark is that so this assumption, so U positive, is important because the theorem is not true if U may change sign. Indeed, there are papers by Ding, 86, and also by Del Pino, Musso, Pajara, and Pistoia, 2011, 2013. Okay, they construct for the Laplacian, of course, infinitely many sign-changing non-radial solution to our problem. So the assumption U positive is fundamental. And while this assumption is, yes, is fundamental, but trying to prove the same theorem is open. Okay. So this was the state of the art related to this important problem. And so our motivations to consider this problem is that the isoperimetric problem, and the Sobolev inequality have been studied in, let's say, more general setting. So not only in the Euclidean space with the Euclidean norm, but also in convex cones of Rn with not the Euclidean norm, but a general norm. So let's say an anisotropic norm. Okay, so let me explain better these two characters of the story. So let's start with the norm. So a norm in Rn is a function h from Rn to R such that H is convex. It is positive one homogeneous. This means that H of lambda psi is lambda H of psi for all lambda positive and for all psi in Rn. And H is positive, so since it is positive one homogeneous, we can say that H restricted to the unitary sphere, this is positive. Okay, so this is the general definition of a norm in Rn, and in particular, we do not require that the norm is symmetric. Okay, so it's very general. And moreover, related to this norm, we define the dual norm is the following. So it is H naught of x is the sup of the scalar product between x and psi, where psi as the unit norm with respect to this new norm. Okay, so this is the norm part of the story. What about convex cones? So in green, cone, so sigma, convex cone in Rn. So a general cone in Rn can be seen as the product of omega times R plus, where omega is a domain inside the unitary sphere, a bounded domain. This is the general definition of cones in the Euclidean space. And but since the cone is convex, this can be seen. So here the convexity is important. This can be viewed as an RK times C, where C is in Rn minus K, is a convex cone with one vertex. So let me draw some picture. So we are considering this kind of cones, of course, with only one vertex, okay, in the Euclidean space, but we are also considering this kind of cones. Okay, so here we have this can be seen as the product of this line times a convex cone with only one vertex. Okay, and of course in our definition we have also the half space, the entire space, and so on. Okay, and so let me mention some papers where this anisotropic, this isoperimetric and the Sobolev inequality have been studied in this context. So of course there is this paper by Leon, Pacella, and Tricarico, 88, and there is a paper by Leon and Pacella, 90. Then there is a paper by Ritore and Rosales, 2004, and also by Cordero, Erasquin, Nazaré, and Villani, always in 2004. For example, in this paper, they study the anisotropic Sobolev inequality in the Euclidean space. Okay, for example. Then there are more recent papers, so the one by Figalli, Maggi, Pratelli, of 2010, and finally the one by Cabret, Rossotton, and Serra, 2016. Okay, for example, in this last paper they studied the Sobolev inequality in convex cones with an anisotropic norm. Okay, so of course many others. So what was the state of the art? So the the Sobolev inequality is the following one. So inequality. So we have that there exists a constant such that we can control the LP star norm inside the convex cone with a constant time the integral. This should be the LP norm, okay, of the gradient. Here we have, of course, h to the power p of the gradient of u, everything to the power 1 over p. Okay, so this is exactly the analog of the Sobolev inequality, but with respect to this new norm and in a convex cone over n. So this was already in literature, and the corresponding Euler-Lagrange equation so if we are in the Euclidean space with the Euclidean norm, then the Euler-Lagrange equation is the critical p-Laplace equation as I showed you before. If one considers this new Sobolev inequality, then the problem becomes the following. We have always a p-Laplace type operator, but is the p-Laplace with respect to this new norm, h of u plus u to the power p star minus 1 equals 0 in sigma. And since we have a boundary, there is a boundary condition, so is a homogeneous Neumann boundary condition on the boundary of the cone. Okay, this is the outer normal to the cone. So where this delta ph of u is the so-called anisotropic p-Laplace operator, so is the divergence of h of a of the gradient of u. So this a is h to the power p minus 1 of the gradient of u, the gradient of h, gradient of u. Okay, so if h is the Euclidean norm, then this gradient of h is nothing but grad u divided by the norm of the gradient of u, and of course you see that this is the divergence of the gradient of u to the power p minus 2, times the gradient, so is the usual p-Laplace operator as before. Okay, so this is the natural generalization to this context. And okay, so the point was that there was the Sobolev inequality, this was known, but was not optimal. So not optimal Sobolev inequality, and almost no results. No results for critical points. Okay, so theorem of classifications to this problem. Okay, so let me mention our result. So we prove two theorems. So theorem 1 is the sharp or the optimal Sobolev inequality in this context. Okay, and of course this leads to the analog of the Oben-Talenti bubbles. Okay, in some sense, with this sharp Sobolev inequality, we classify, we did the analog of the works by Oben and Talenti. We classify the minima of the functional. So it is natural to ask whether a classification results or not, and this is our theorem 2. So theorem 2 is the characterization of solutions to. So this problem, we have the Euler-Lagrange equation, so it's the anisotropic p-Laplace operator plus u to the p star minus 1 equals 0 in the cone, and of course we have the Neumann boundary conditions. And we classify, so positive solutions as before with finite energy. Okay. Okay, so this is exactly the analog of the theorem by Caffarelli, Gidas, and Sprack, and by Vetois and Schunzi. Of course, we have the hypothesis U positive, and also this hypothesis of finite energy. And okay, so this was just a summary of the results. So let me explain them better. So let's start from theorem 1, which is the sharp Sobolev inequality. So let P between 1 and n, sigma a convex cone in Rn, and H a norm. So the same setting that I introduced before. Then for any f with finite energy, the following also. We have the Sobolev inequality. So f, the norm of f, Lp star sigma is less than a constant times, here we have h to the power p of the gradient of f, to the power 1 minus p. Okay, this is the Sobolev inequality, was already known, but what we are able to prove is that, moreover, the equality holds if and only if f is equal to these anisotropic Oben-Talenti bubbles, where this function is given by this expression. So I put here an h to remember that this is anisotropic. Okay. So it's exactly as before. Here we have a constant that depends on lambda, on n and p, and also on h, divided by lambda, the p over p minus 1, plus here we have the dual norm of h naught minus x naught minus x to the p over p minus 1, everything to the power n minus p over p. Okay, so these are exactly the analog. If we consider the Euclidean metric, then the dual norm is exactly the Euclidean metric. So we recover the result by Aubin and Talenti. And this point here, x naught, if we are in Rn, this is free to be any point in Rn. But in this context, we can say that x naught should be the vertex of the cone, because the vertex, if there is one or if there is many, should be on the line of vertices. But this can be understood because we have the Neumann boundary condition. Okay, so in order to be satisfied, we have to put this x naught on the vertex of the cone. And the proof of this result, so proof by optimal transport. So we use the optimal transport to prove this sharp Sobolev inequality, and one can see the paper by Cordero, Erasquin, Nazaré, and Villani that I mentioned before. Where they prove, by using this optimal transport approach, the anisotropic sharp Sobolev inequality in Rn. Okay, so we do it in this context of convex cones. Okay, so this is the first theorem, and the second theorem is a Liouville type theorem. So theorem 2 is the following. So as before, let n bigger than 2, p between 1 and n, sigma a convex cone over n, of course, h a norm, and here we have to assume that h square is in C2 of Rn minus the origin, and is C11 everywhere. And I will comment a little bit this assumption, and uniformly convex. Okay, so we have a cone, a norm sufficiently regular, let's say, and then let U a solution to the problem of before. So we have the anisotropic p-Laplacian plus U to the p star minus 1 equals 0 in the cone, the Neumann boundary condition. On the boundary, U positive and U with finite energy. So if let U be a solution to this problem, then U of x is equal to an anisotropic Aubin-Talenti bubble. Okay, and so this is a classification result, exactly as the same that I showed you before. And so some comments, remarks. So the first one is that on the assumption, so sigma is just a convex cone in Rn, and we have weak assumptions on H. Okay, this is very general, this the theorem. And okay, before I mentioned that there was almost no results for critical points. So actually for p equal to and h, the Euclidean norm. Okay, so for the Laplacian, for the usual Laplacian in a convex cone, there was already a result like this in the paper that I mentioned before by Lyon, Pacella, and Tricarico. Okay. Also in this case, the assumption U positive is important because, so as before, this is not true if U may change sign. And one can see the recent paper by Clapp and Pacella, where they construct infinitely many non-radial sign-changing solution to this problem for the Laplacian, for the usual Laplacian. But so it's the analog of the papers by Ding, Dempino, Musso, Paccara, and Pistoia. So it is important to assume this. While of course this assumption would be interesting to remove it. And okay, so another remark is that our proof is not based on the method of moving planes for two reasons. So we are in a convex cone, so the method of moving planes is, let's say, is hard to apply in the standard way. And also because we have an anisotropic operator, so the method of moving planes is not the right tool to use. So the proof is by integral inequalities. And it is let's say the spirit is similar to the one by Gidas and Sprack 81 and Serin et Zhu 2002, where they prove so they prove non-existence result related to this kind of critical p-Laplace equations. Okay, so it's a different, is a slightly different context, but the ideas are similar. And this and our proof is new also for, let's say, H, the Euclidean norm, and sigma are n. So we provide a new proof which actually is suitable to be applied in this conical and anisotropic setting. Okay, and so finally, another important thing is that probably our proof is suitable to be generalized also in a Riemannian setting. So this would be interesting. So this is new, and also, let's say, Riemannian setting. And so we are working in collaborations with always Giulio Ciraulo and Rosario Corso from the University of Palermo in Italy. We are working on non-existence result related to this kind of problem. So these non-existence results are similar to the one proved by Gidas and Sprague that I mentioned before. And okay, I think that this is all that I want to say. And yes, I can stop here, and thank you for your attention.
Okay. Thank you.
La grabación se ha detenido.
Thank you, Alberto, for your nice talk. Are there questions? Well, I don't see questions in the chat.
Hello?
Yes,
Hello?
yes.
So this is Jyotsna Pradapat. I thank Professor Ortega for allowing me to attend this talk. I had a question here, like, did you say that this result is also true for Rn? Like for p-Laplacian case, without your proof works for that?
No, we we need this assumption also in Rn. You mean this hypothesis, right? If I
Yes.
understand correctly, this one. So this is fundamental also for our approach.
Okay, okay.
Yeah.
But the Liouville theorem for p-Laplacian on whole of Rn, so it is similar, but your proof is different. That's what you mean to say.
Exactly. We didn't use the moving planes.
Okay, okay, fine.
Yes.
Yeah.
Yes.
Thanks.
Thank you for this question.
So, other questions? Well, I have a little question. I'm just curious about why the name of bubble for the Aubin Talenti function.
Yes, I think that because
does it come from any scaling approach or something?
Yes, I think that the names come from because they are something like this, you know. I think, but I don't know exactly where it come from, these bubbles. Actually, in the paper by Talenti, I'm pretty sure that he didn't mention the name bubbles are functions, but yes, probably is related to some work by Struve, where they study qualitative and quantitative property related to the critical Laplace equation in Rn. Yeah, is related to something like this. Should be.
I think that maybe it is because when they do this blow up analysis, and like as you already mentioned, for the conformal case, this correspond to the sphere.
Right.
The
yes.
metric on the sphere. So I think maybe in geometry they probably call it bubbles, means not in PPE. Yeah. So maybe that stuck on. So yeah. Yes.
Yeah. So should be something like this. Yes.
Okay. Good. Any other comments?
Yes, I have a question. This is Pablo Mira here. Hi, Alberto.
Hi.
I wanted to ask you about the two-dimensional case, which in principle is contained in all the discussion that you mentioned here. But if you look at least at the case of p equal to 2, so the scalar curvature case, constant scalar curvature case, so you have like two different situations in that setting, depending on whether the dimension is 2 or is higher than 2. So for higher than 2, it's well understood by this type of theorems. For dimension 2, in order to classify the solutions, somehow you need to impose some integral condition, like finite energy or something similar.
Yes.
Where you have too many. So if you go to dimension 2, in this case, so n equal to 2, so p should be between 1 and 2, right?
Yes, exactly.
Do you have something else there? Can you, I mean, maybe you can somehow remove the hypothesis that u is positive under some integral finiteness assumption or something similar?
Yes, this is
something more. Do you know anything in that line?
Yeah, this is of course an interesting question. I don't know the answer, but yes, I know the result that you are mentioned, this kind of result, but I don't know. Should be interesting to investigate more about this special case. Let's say n equal to. Yes. Okay. Thank you.
The other thing, just a remark. I would say that maybe this PDE is more related to not to the Yamabe problem, but to the Nirenberg problem. The Nirenberg problem is basically the same equation, but asks exactly that for conformal metrics on Sn, which have constant scalar curvature. So it deals with the case where the initial metric is locally conformally flat. So I mean, maybe it's the same equation, but a bit different perspective. I think it relates better to the Nirenberg problem.
Okay. Thank you. I didn't know this problem. Okay, thank you.
Very interesting results.
Okay. Thank you.
Other comments then? I don't see any other in the chat. So thank you very much, Alberto, for your talk and your answers.
Thank you. thank you to everybody. It was a pleasure.
Bueno, pues yo creo que aquí podemos despedir, Miguel, si no hay algo más que anunciar. Vale. Muy bien. Hasta luego a todos. Adiós.
Bye bye.